So good morning. Good morning, people. Now it's
Good morning.
Good morning.
yeah, thanks. It's now 9 o'clock. Now we can start from where we stopped last time, and we were going to talk about the dielectric slab in free space. That is, before we have seen a dielectric slab that is placed on a ground plane. Now this just says the same kind of problem, but now we don't have a ground plane, but the dielectric is finding itself just immersed in another dielectric medium, such as air or free space. So we are, like I said last time, when we look at round dielectric media or round wires, we have to use the base of functions. And whenever we are trying to compute, say, for example, power such as the Poynting vectors and the like, what would happen is that we'll have to deal with integrals of the base of functions, which is a highly mathematical, you need a lot of effort in mathematics, and it will hide the detail or the principle that it is that we want to point out. So what we are going to do is that we are going to assume that we have a planar dielectric slab, and this dielectric slab finds itself in free space, and we consider the slab to have a thickness d with the constitutive parameters epsilon and mu, and sigma equal to 0, therefore making it a perfect dielectric slab, so to speak. Now, for simplicity, we will assume that there are no variations of the fields in the x direction, and the propagation factor is of the form exponent of j omega t minus gamma z in the z direction, which we have chosen to be the axis of the dielectric slab. So that's for Ez. Then Ez is going to be a solution of Helmholtz equations in two regions. That is, inside the dielectric, we'll have it being a solution with a value of Kc equal to Kd for the region y less than d by 2, that is the modulus of y. And outside the slab, we'll have the Kc, or the cutoff wave number, being equal to Ka, which is representing the cutoff number in the air region. So hence, we can express Ez as a superposition of two types of fields. One we call the odd field, and the other an even field, in the following form. That is, Ez of y is going to be given by E naught or EO, or odd, sine Kd of y plus E of E and cos Kd of y. The reason why we are calling them odd and even functions is because we can see that sine Kd of y is going to be negative when y becomes negative. That is, in the region y less than minus d by 2, that function is going to be negative. And in the positive direction is positive. And therefore we see that it's an odd function. And the E of E, that is cosine of d, is going to be positive for both negative y and positive y. And therefore we find that cosine of d is going to be maximum at the axis, while the odd function is going to be 0 at the axis. So Kd has been defined as k squared minus beta squared, where k squared is of course the propagation constant in the dielectric, which is assumed to be of infinite extent. So this relation is therefore called the dispersion relation for the dielectric media. In the free space regions, that is for y outside the d by 2, the waves must decay exponentially, because we expect that we want our dielectric to guide the waves, and therefore we want the waves only to follow the guide or the dielectric, and therefore we expect that no leakage occurs. That is, the fields must decay exponentially in the y direction, so that they are not radiated away from the dielectric, and then we can say that the dielectric is guiding the waves themselves. Thus, we can write that Ez is going to be given by the exponent of Ea exponent of minus alpha y minus d by 2 in the y greater than d by 2, and EB exponent of alpha y plus d by 2 below that is in negative y direction, that is when y is less than minus d by 2. And here we have defined alpha square as the minus of k a squared, so that we get it to be given by beta squared minus omega naught mu naught epsilon naught, or that is the k naught, which is the propagation constant in free space. Now, continuity of the Ez across the interface at y equal to d by 2 and minus d by 2 then will yield solutions of the form Ea E naught of sine k d by 2 plus Ea cos k d by 2. And Eb is going to be given likewise by the values where we say that for the odd functions, that is going to be the negative, while that one remains a positive value. So we consider the three regions separately so as to simplify the analysis. Now, in the electric region, we have that Ez of y is going to be given by E naught sine kd of y. And Ey is going to be given by the minus of j beta kd E naught cos kd of y, where we are just looking at the odd Tm modes that would be propagated by that guide. And h of x is therefore going to be given by j omega epsilon by kd and E naught cosine kd of y. So in the region y greater than d by 2, of course, all we have is those expressions. Again, all we have to do is to replace them by the value of the d and also the value of the Ea and Eb's. And we get those kind of solutions there. And in the region below the dielectric, that is in the minus y direction, then we have similar values of that nature. So this is just algebraic, and there's nothing much we can say about it, because there's the algebraic with just manipulation get the values that we are dealing with. So the continuity of hx at the dielectric interface then requires that hx d of y at d by 2 have the same value in both free space and the dielectric itself. And thus, we can set those values at kd at d by 2, and we'll get a value of epsilon by epsilon naught multiplied by alpha. I'm multiplying by alpha here directly so that we can see the values happening. And we get that alpha r of alpha will go to kd tangent of kd and multiplied by d by 2. And from the dispersion relation, we see that alpha squared plus kd squared must be equal to omega squared into mu epsilon minus mu naught epsilon naught. And this, we can always write it as alpha equal to that value. Remember that mu epsilon, mu multiplied by epsilon minus mu epsilon naught by epsilon naught is the same as mu epsilon naught multiplied by mu naught epsilon naught multiplied by 1 minus, or epsilon r minus 1. That is that whole thing, where epsilon r is, of course, the dielectric constant of the dielectric. So we combine these expressions to obtain a value of that nature, where we are using ky squared, and this must be equal to kd by epsilon r and the tangent of kd by d by 2. And we note that for the odd modes, Ez of y is equal to 0 at y equal to 0, and then we can therefore, without changing the field distributions in the dielectric, we can introduce a conducting plane along the axis or the axial plane of the dielectric without affecting that distribution of the fields. And therefore, odd Tm modes propagating in a dielectric of thickness d are therefore going to be the same as those that would be propagating on a slab of thickness d by 2 that is backed by a conducting plane like we saw last time. So the surface impedance, looking down on the slab surface from, that is, we are looking from the y equal to infinity direction, then will be given by Zm equal to the minus of Ez by Kx, Hx, which this representing the transverse transverse fields in that direction when we are looking down the y-axis, and this is going to be given by J alpha by omega epsilon naught. And we see that this is an inductive impedance, and therefore it means that an inductive surface will support an odd mode surface wave. For the even Tm modes, then Ez must be just given by E of E and the cosine of Kd of Y, which gives us for that region inside the dielectric, and we can use the same values for the outside the dielectric as well. So on invoking the continuity equations at the dielectric surface, we obtain that alpha r, epsilon r multiplied by alpha is equal to the minus of Kd and the cotangent of Kd d by 2. Remember, for the odd modes, we had a tangent function. And the phase constant for the propagating even Tm modes then lies between the intrinsic phase constant of the free space and that of the dielectric, like we saw before. And this omega, that is omega multiplied by mu naught epsilon naught, which is just k, that is k naught, must be less than beta, where the beta is the phase propagation constant of the waves, and this must be less than the k of the dielectric. So as beta is made to go towards the k naught, we find that alpha will tend to go to 0, and therefore if alpha is equal to 0, then it means that the waves outside the dielectric will no longer be attenuated, and therefore they propagate. And therefore we can say that the wave will no longer be confined with that dielectric. And therefore, the condition beta going to the value k naught or alpha going to 0 is going to represent our cutoff frequencies or our cutoff conditions for the dielectric slab. So the limiting frequencies under these conditions are the cutoff frequencies of the dielectric waveguide. So at cutoff, we therefore have for odd Tm modes and the tangent of omega C naught, that is the cutoff frequency, radiant frequency for odd modes, multiplied by d by 2 and multiplied by that k naught into root epsilon r minus 1 must be equal to 0. Or in other words, we can write that in terms of the cutoff frequency fc naught is given by that value, and we say that it must be equal to the odd or integers of pi, where n is equal to 1, 2, 3, and so forth. And therefore, fc0, that is for odd Tm modes, the cutoff frequency is just going to be given by n minus 1 over d root mu naught, mu epsilon minus epsilon naught, and mu and epsilon r. And for even modes, the cotangent is the one which we are going to set to equal to 0 because we want alpha to be equal to 0. And therefore, we can see that the cutoff frequency for the even modes is going to be given by n minus a half of the divided by d and root mu epsilon minus mu naught epsilon naught. And we note that fc odd is equal to 0 for n equal to 1. And therefore, it means that for the dielectric medium, the lowest odd Tm mode will propagate along the slab regardless of a slab, the slab thickness. And in the case of Te modes, at a source-free point Hz, that is a solution of the homogeneous Helmholtz equations that are given by that solution there, or that equation. Remember, if you look at these equations, the Helmholtz equations here are similar to those of the Tm modes, only that we replace the fields with the axial component of the magnetic field intensity rather than the electric field intensity. And therefore, in a similar way, we can always have Tm modes, or a similar way to Tm modes, we can express the general solution in terms of odd and even components as shown below. And we can therefore write that for odd modes in the dielectric region, we then have Hz being equal to h odd sine ky, and hy equal to the minus of j beta by kd, ho, and cosine kd and y. And ex will of course be given by that expression. This of course being obtained from the reduced Maxwell's equations. So in the region y greater than d by 2, that is the modulus of that, then we have that hz is going to be given by that expression there, and we expect that as y increases towards infinity, this exponent goes towards minus infinity, and therefore the hz decays to 0 as y goes to infinity. And the same, and hy will also have the same kind of variation, as so will ex as well. And therefore we see that outside the dielectric, the fields are decaying, and this, you remember, are what we call the evanescent waves that we were talking about the last time. And in the region y less than minus d by 2, the expressions are the same, and we'll replace those ones by the alpha positive values because y is negative. So at y equal to d by 2, the continuity conditions then yield the following equation, that the relative permeability of the dielectric multiplied by alpha is going to be kd tangent of kd by d by 2. And looking on this surface from the y equal to infinity, we see that Zm is going to be given by Ex by Hz, and we see that it's going to be the negative of j omega mu naught by alpha, and because of the negative sign here, we can see that this is a capacitive impedance. And therefore, we say that this is a capacitive impedance, but what we can notice is that for a capacitor, we expect that the impedance should be decreasing with increasing frequency. But for this particular case, we see that while it's capacitive, it's increasing with frequency, which is an anomaly, so to speak. So a capacitive dielectric surface will therefore support a TE surface wave. So for even TE modes, we have that Hz is going to be given by He and the cosine of kdy in the dielectric, and we can write that mu r of alpha will be given by kd, the cotangent of kd multiplied by d and divided by 2. And the lowest odd TE mode will therefore have no cutoff frequency. So, example 1. A dielectric slab waveguide with constitutive parameters mu d equal to mu naught, epsilon d equal to 2.5 epsilon naught is situated in free space. Determine the minimum thickness of the slab so that a TM or TE wave of the even type propagates along the guide at 20 gigahertz. The lowest even TM mode and the TE mode have the same cutoff frequency of FC equal to n minus 1 over half there, and given by that value. And thus, for n equal to 1, we have that f of c is going to be given by c by 2d and the root of epsilon r minus 1. And therefore, the minimum thickness we can have is d min going to be given by c followed by twice fc and the root of epsilon r minus 1, and get a value of 6.12 centimeters. This you can always ascertain for yourself. So, part 2. Obtain an approximate expression for the decaying rate of the dominant TM surface wave outside a very thin dielectric slab waveguide. And 2. Determine the time average power per unit slab width transmitted along the guide. And C, we are expected to answer the question, what would be the time average power transmitted in the transverse direction? So, the first thing is that to note is that FC of O, that is the lowest cutoff frequency for odd modes, is going to be 0 for n equals to 1 and for all d. And if kyd by 2 is much smaller than unity, you can always have that the tangent of kyd by 2 will be approximately equal to ky by d by 2 in radians. And thus, the alpha is just going to be given by a half of epsilon naught by epsilon d and ky squared and multiplied by d, and this gives us a value of that nature multiplied by d, where we have assumed that alpha d by 2 is also much smaller than epsilon d and epsilon naught. And part B, we can see that the power average, that is the time average power or Poynting vector, is going to be given by a half of the real part of the cross product of EY cross HX star, that is the conjugate. And thus, when we do that, when we get the average power is going to be over the cross section, and the cross section, of course, it's because we are using per unit dielectric width. So we are assuming that the width of the dielectric is unity, and therefore we don't have to integrate in that direction, because, as we said, there were no variations in the x direction. So we have this integral from 0 to d by 2, and multiplied by integrating the average, the time average Poynting vector in the y direction, and we get a value of that in watt per meter. So ky will then be approximately given by omega into mu d epsilon d, where these are the parameters for the dielectric, and those are the free space parameters. And beta, we are going to be given by approximately that value. So, let's see, since h of x is pi by 2 out of phase with Ez, then we should get that the time average Poynting vector is going to be equal to 0. And therefore, there will be no power propagated in the transverse direction. Now, if we consider this dielectric as shown here, and we are launching a field or a wave at an angle theta I to the normal vector on the surface of the dielectric surface. So we consider the plane wave incident on the lower surface of the slab at an oblique angle of incidence. So the total internal reflection will occur if epsilon is greater than epsilon naught, and theta I is greater than theta IC, where you recall from last semester that theta IC was what we call the critical angle for which the field, there will be no transmitted field outside the dielectric, especially when we have the wave incident on an dielectric interface from the more optically dense material than the other. So theta I will be the critical angle of incidence, and will be given by theta I of C because the arc sine of root epsilon naught divided by epsilon. So an evanescent wave will be set up on the surface as well. So the reflected wave will be incident on the upper surface at an angle theta I, and will therefore suffer total internal reflection as well. And the two plane waves incident on the top and lower surfaces will hence interfere and establish an interference pattern, which we usually refer to or call it a mode pattern of the propagating wave. So Tm and Te decomposition then requires that the fields have circular symmetry, that is, they must be independent of phi in circular waveguides. And if phi dependence exists, then we must consider the hybrid mode solution. So we consider a conducting plane that is backed by a slab as shown below. Now this is exactly like what we started with there. That is when we are looking at in homogeneously filled parallel plate transmission line. So we shall see that this is exactly what we dealt with when we let the upper plate go to infinity. The reason I'm giving this a second time is so that we can see the actual analysis of these values, because I guess the way we approached it previously may have been a little bit more, might hidden the detail. So the dielectric coating will have a thickness A given by D by 2 and is of infinite extent in the X Z plane as is the perfectly conducting ground plane as well. So we consider Tm waves propagating in the Z direction with a propagating factor of the form exponent of J omega T minus beta Z. And we assume that the wave is to be confined to the dielectric region and the fields do not vary in the x direction. Such a situation would happen, say, for example, when we have a dielectric coated on a vehicle body. Say, for example, the paint, and we want the paint to be to guide the wave, so to speak. So we know that the paint will be a dielectric, and the car body, which is usually, unless you are getting this energy efficient one with the carbon fiber bodies, and you are using that normal steel bodies, then you can have a conductor there, so to speak. So at a source-free point, Ez will be a solution of the homogeneous Helmholtz equation that is given as Kc equal to Kd in the dielectric and Kc equal to alpha in the air region or outside the dielectric. And the reason we have written this is because from the previous discussion, we have seen that we require that the fields decay away from the dielectric as as they distance away from the dielectric for the wave to be confined in the dielectric region alone. So Ez must therefore vanish at y equal to 0 because we have a conductor there, and y equal to infinity because we expect the Sommerfeld radiation conditions to apply, and because of the way we have written it as alpha. And therefore, Ez is going to be given by En sine k dy in the region 0, y, and a, and Em exponent of minus alpha y minus a for the region y greater than a. And the continuity of the tangential electric and magnetic fields at y equal to a will then require that the propagation constants in the two regions be exactly the same. And this, you recall, is what we call phase matching of the two waves in the two regions. And thus, the dispersion equation is given as beta squared equal to k squared minus kd squared equal to k naught squared plus alpha squared. Or in other words, we can always write that as epsilon r minus 1 multiplied by k naught squared equal to kd squared plus ka squared. Remember, Ka and Kd are the cases for the propagating waves. So the continuity of Ez across the air dielectric interface then will yield that Em is going to be given by En and the sign of Kd multiplied by A. And the transverse field components are then going to be given by E of t equal to minus j beta by Kc squared, the gradient of Ez, and we get a value of that inside the dielectric and that value outside the dielectric, where we have already used the value for Em and as En sine kdA multiplying the exponential function, and we see that as y goes to positive infinity, this wave will be decaying. And h of t will be given by that value there, which is in the dielectric, and that value in the outside the dielectric, again decaying as y goes towards infinity. So the continuity of hx at y equal to a then allows us to write that kd of a multiplied by the tangent of kd of a is equal to minus alpha r epsilon r alpha multiplied by a. Now notice here I've just multiplied through by the dielectric thickness so that we can get these values looking alike. Okay, so we have multiplied through by the dielectric thickness to get that value there for the continuity. This is normally not there, but you can always multiply. As long as you multiply both sides with the same factor, then you have not defied anything. And when a solution for real alpha exists, this will be a surface wave, since its field will decay exponentially in the y direction while propagating in the z direction. And the eigenvalues for the Tm surface wave problem can be obtained more directly through the transverse resonance technique that we have already looked at before. And this is an application of the transmission line theory to the equivalence circuit of a transverse section of the guiding structure, and is applicable to the waveguide that has uniform cross-section in the direction of propagation. So we consider the surface waveguide viewed along the y axis as shown below. That is, we are looking, our guide itself is moving, it's actually proceeding in the z direction, and we are looking at it from the y direction. So we are looking at y going that way, and therefore this is the value of A, and that is the X is coming out. So all we have done is to rotate our dielectric structure that we were looking at before, so that we can be looking through the y direction to illustrate how this transverse resonance technique operates. So the propagation constant in the y direction is then going to be given by J multiplied by KD in the dielectric and alpha in the air region. And thus, the wave impedance for the wave propagating in the y direction is going to be given by ZTM of y is equal to KD by K and multiplied by the intrinsic impedance of the dielectric, and ZTM of y equal to alpha by JK naught multiplied by eta naught in the air region. And the equivalent circuit is then a short-circuited transmission line of length A and impedance J alpha epsilon naught by divided by K naught. And at the reference plane, the resonance condition then requires that the sum of the impedances seen looking toward the short circuit and the input to the infinite line then vanish, just like we said. And therefore, we must have that J, KD by K eta, tangent of KD of A minus J alpha by K naught eta naught must be equal to 0, or in other words, we get the similar equation like we had before. So this is another technique in which you can use to analyze that particular value. You should get the same value. Now remember, this is exactly the same value that we already obtained if we multiply that by A and A or throughout by A, which is the dielectric thickness. So for the TM0 mode surface wave, it will have no cutoff frequency, but this is not a characteristic of all the surface wave guiding structures. And these structures will have only a finite number of propagating modes at any given frequency, unlike the things we saw for the waveguides that we were looking at before. They had infinite number of propagating modes, but this will have only a finite number. And when the mode exists, its phase velocity will be lower than the plane wave velocity in air, because we have that Vp equal to K naught by beta and multiplied by C, and this will give us a value of K naught over K naught square plus alpha square and multiplied by C, and we see that this is going to be smaller than the velocity in air. And for this reason, the surface wave will always be referred to as a slow wave. And there are a lot of devices that have been designed for this kind of operation, and we call them the surface wave, surface acoustic wave, whatever, filters and the likes, or what you would call SAW. So consider a circularly symmetrical TM mode in a circular dielectric rod of radius alpha, radius A and permittivity epsilon situated in air. So this is an introduction of the cylindrical waveguide, which you'll get as a fiber optic in common use in communication. So the transverse distribution of the axial field components of the electric field intensity Ez for TM modes in the rod is going to be given by Ez of I equal to En multiplied by the Bessel function of the first kind and order 0, and in the dielectric, that is for radius less than A, and where the Kc, that the cutoff frequency, is going to be given by gamma squared plus K squared, which is equal to omega squared mu naught to epsilon minus beta squared. For propagating modes, we know that gamma is going to be equal to j beta. So the corresponding circumferential magnetic field intensity, which is h phi of I, is going to be given by h phi of d equal to j omega epsilon by kc and multiplied by that value, where we have just used the derivative of the z. So outside the rule, the fields must be evanescent, and we may choose the modified Bessel function of the second kind and order 0 for the solution. That is, we must have that Ez of A be equal to the derivative of that is En prime, that is just a new impedance or a new amplitude, multiplied by the Bessel function of the second kind, that is modified, and order 0 for that value. And remember, the Bessel function or the modified Bessel function is actually the actual Bessel function with the arguments that are imaginary. That is, we have a j value, and where the alpha squared is going to be given by that expression. And h phi in the outside in air is going to be given by j omega epsilon naught and multiplied by an amplitude d naught and the derivative of k naught alpha r. So Ez and h phi must be continuous across the boundary, that is the dielectric air interface, which is circular at r equal to a. And hence, we must have that E and J naught Kc of A must be equal to that value inside the dielectric, and that the magnetic field intensities must be equal at the interface. And therefore, when we combine these two, we get a value of that nature and another value for the J naught by J naught prime, that is the derivative, and K naught prime is the derivative of K naught 1 of alpha r with respect to r. And Kc squared plus alpha squared is equal to that value, which we call this is from the dispersion relation. And commercially available optic fibers will usually be of two types. One, we can have one fiber that is called a step index fiber with a homogeneous central core dielectric, which is the guiding region of the guide, and an outer sheath of a material with a lower dielectric constant. This is done so as to reduce the radiation or the leakage of the wave that is propagating in the central region. Okay, we have seen for the dielectric guide to guide the wave, then it must have a higher dielectric constant than the surrounding medium. So then we can have another one called the graded index fiber. It's more like those of us who use specs. There's what you call progressive lenses, that the refractive index is changing along the axis. So for the graded index fiber, the dielectric or the refractive index of the dielectric is allowed to vary, that is to decrease from the central region towards the outside or towards the periphery of that particular dielectric. And therefore, we call it an inhomogeneous relative index, refractive index profile. So a typical fiber will consist of a guiding core region of a high dielectric constant, that is high refractive index, and it's surrounded by a lower refractive index, which is called the cladding region, especially when we are dealing with the stepped index fiber. We'll have the core and the cladding. So a typical commercial optic fiber will be illustrated as shown. The plastic is used for, you have seen the yellow plastic. I'm sure for those of us who have been keen around the electrical engineer American way, they're always digging up the yellow cables and the likes. Those are the fiber cables. They usually have a yellow plastic covering to protect, for protection. Then this would be a lower refractive index cladding for the fiber, and that is the core of the fiber. So this will be a step index cylindrical dielectric medium, or a waveguide, or the optical fiber. So within either the core or the cladding region, the phase propagation constant must be the same so that the axial electric and magnetic fields satisfy the Helmholtz equations that are given in that form, where we have now expressed the Kc squared in that form. Or in other words, we must have that the gradient, or that is the Laplacian of E of z, is equal to that value, where n is equal to the root of epsilon r whenever the material is non-magnetic. Mu r is going to be given by unity, and therefore the refractive index is just simply the square root of the dielectric constant. So an intuitively important consideration is that Ez does not couple to the other two components even after reflection at the cylindrical surfaces as the electromagnetic wave propagates. Because if it does that, then we'll have power leakage into the other components. And therefore, since Ez couples only to itself, the wave equation for this field component can be expressed in cylindrical coordinates as shown below, where we have now reduced the Laplacian square into the cylindrical coordinates to get that value there. So if we assume Ez to have the form Ezr of phi equal to Ezr exponent of Jm phi, then that is into a radial function and an angular function, okay? Then the radial equation of function is then a solution of the Bessel function of that nature. And we notice that this is going to be the Bessel function, so to speak, of the Bessel differential equation. And thus, as long as the cutoff frequency Kc is equal to that, is greater than 0, the valid solutions are going to be the Bessel functions of the first kind and having an order m, as the fields must remain finite at the center of the core, okay? Because the core is included in the solution space because we are dealing with a dielectric, and the Ez can only be 0 at the center only if we have a conductor there. So when K naught squared multiplied by the refractive index squared minus beta squared is less than 0, the valid solution will be the modified Bessel function of the second kind, because the fields must vanish at infinity, where alpha squared equal to beta squared minus K naught squared m squared. Remember, the Bessel function, the modified Bessel function of the first kind I, which we call I of m, increases with increasing radius or increasing distance r, okay? While this, for the second kind, it decreases with increasing radius. And therefore, that's why we are saying that the valid function there to use for this particular case would be the second kind. And for the guided mode, beta must be such that the propagation constant in air multiplied by the refractive index of the core be greater than the phase propagation constant beta, and that be greater than that K naught multiplied by the refractive index of the cladding material. That is, the propagation constant in the core must be greater than the phase propagation constant of the wave at the operating frequency, and this must be greater than the propagation constant in the cladding material. So, and therefore, within the guiding layer, that is the core, you can write that the Ez is going to be given by that multiplied by the Bessel function of the first kind and multiplied by the angular function there, and the Hz is going to be given by that value for the r less than a. And outside the core, you must have those expressions there varying by that alpha r. So the coefficients A1, A2, B1, B2 are then determined from the continuity condition for the tangential components or the tangential components of the fields. And from the curl of E equal to the minus j omega mu naught of H, we can therefore write the field components as shown there, where we have just used these values, the curl equations, and in the core, we have those kind of values. These expressions, of course, they look quite weird, and that's why we didn't want to look at the round or whatever dielectric media or slabs. And in the cladding, that should be the same kind of expressions. And on matching the boundary conditions, we'll get a value of that nature. This must be equal to 0. That is, this must have, this determinant must have vanish for us to get a value of that value. I think what is missing is the A1, A2, B2 equal to 0, so to speak. And I try to correct that in the slides when I finish. So the characteristic equation from which beta can be determined is then going to be given by that value there. Remember that this value is the determinant of this weird looking 4x4 matrix. So we then have that B1 is going to be given by that value, and B2 is going to be given by that value there. And on using the continuity of the electric field, you can get the A1, A2 in terms of A1, and or using the continuity of the magnetic field, you can get it in that form as well. So when you are dealing with, when you'll be dealing with, say, for example, communication circuit or wiring, you'll most likely deal with wires that are round with a dielectric insulation. This is something we have seen in the lab all the time, those connecting wires you use with the breadboards. So if you were to look at them in terms of the very high frequency operation, then they would appear like as shown, that will have a conductor surrounded by a thin layer of plastic, which is usually PVC, of thickness B minus A. So for circularly symmetric E modes, we can let that Kc equal to Kd in the dielectric and Kc equal to Jka in the air region that is surrounding the structure. And since dd phi is equal to 0 for the circular symmetry, then Ez will be a solution of the Bessel function of that nature. And in the region A, less than R, less than B, Ez is generally a linear combination of the zero order Bessel functions of the first and second kinds, because the origin is not in the region of interest, because it has been removed by the conductor being there. It has removed the R equal to 0 point, and therefore we must have the second kind also coming in. And thus, we can have that Ez is going to be given by A1 J naught Kd of R plus A2 Y naught Kd of R. And in the region R greater than B, the field must be decay with increasing R to correspond to a surface wave as we are looking at. And we recall that for large KR, we can always make the approximation that the Bessel function of the first kind and order 0 approximately goes as 2 over J pi KAR and the cosine of JKR multiplied by minus pi by 4, and the y of 0, that is the Bessel function of the second kind and order 0, will approximately be given by the sine value of that. They have the same amplitude. Hence, the superposition will give us a value of that nature, which is the Hankel function of the second kind. I think there must be a problem here somewhere. And order 0. And the Bessel functions with the imaginary arguments can be replaced by the modified Bessel function In y and Kny, defined as In of y equal to j minus n by jnj of y, and the Kn, that is the second kind and the first kind, and we get the value of the following. So this will decay exponentially with increasing y, making it a suitable solution for E of z in the region R greater than B for that dielectric coated conductive wire. And In of y increases, and therefore we can ignore it when we are looking for physical solutions or physical fields. But if we are just being mathematicians, we can always allow it to be part of the solution. And thus, E of Z is going to be given by that value there. And since Ez is equal to 0 at R equal to A, that is, we have a perfectly conducting wire, that's what we are assuming, then it must be necessary that A1 of J0 Kd of A plus A2 Y0 of Kd of A equal to 0, or rather, we can have the value expressed in terms of A1 alone. And continuity of Ez at R equal to B then allows us to write that that value is equal to those values coming from the inside of the dielectric. And from the dispersion relations, then we obtain a value of Kd squared plus Ka equal to epsilon R minus 1 multiplied by the K0 squared. And the tangential field components will then be given by the derivative or the gradient of Ez, which we just differentiate those values. And H of t will be given that, where we have used a wave impedance for Tm modes as beta by omega epsilon, which is always given. We have already defined that. And we have therefore Kc equal to Kb inside the dielectric and equal to J Ka outside the dielectric. And thus, E of R is going to be given by that value there. H phi is going to be given by that value there. And when we invoke the continuity of H of phi at R equal to B, we obtain those values. Okay, that is outside the air, and this one inside the dielectric, and we get that value there. And when D is equal to B minus A, much smaller than A, where remember A is the radius of the conductor, then that can be expanded about Kd of A in a Taylor series, and we get a value of that nature. And since A is much smaller than the wavelength in air for a typical surface waveguide, then Ka of B will be small whenever D is a small value. And hence, we can always write that function K0 of Ka is approximately the natural log of 0.89 multiplied by Ka of B. And the other value, the derivative, is just going to be approximate 1 by Ka multiplied by B. And therefore, these values, when we use the relations, we'll get those values happening or coming into play. And as an example, we can have a copper wire, which is the usual copper wires, with A equal to 0.09. I don't know, this one is about 0.9 millimeter. That's a large copper wire for wide power. And B is about 0.1 centimeter. And D is going to be 0.01 centimeter. So epsilon R is going to be given by 2.56. And epsilon, this would be Teflon, I think, or something like polythene. And lambda naught is going to be given by 3 by 1.4 centimeters. So Ka is approximately 2.58 NEPA per centimeter. K naught will be approximately 2, and Ka squared will be much more by K naught. And we see that beta is just about 2.02 radians per centimeter. So when Ka of R is large, we can always approximate the K naught Ka of R with that expression. We see it's a decaying exponential. And hence, at R equal to 2 lambda naught, the field will be down by a factor 0.052 from its value at R equal to B, and therefore we can see that it's becoming very, very small indeed. And therefore, the effective waveguide will therefore be given by a guide that is about 4 lambda naught, and the surface waveguides are therefore practical only when we deal with high frequencies, because if we are to deal with a low frequency, then the lambda is going to be large, and since the effective guide should be 4 lambda naught, then you can see that the waveguide will be very, very large indeed. Another thing we can see is, of course, when we look at radiation, we can see that the ionosphere is a conductive layer in the atmosphere. That is where we have ionized gases, and the Earth itself is is approximately a sphere, and it's usually a conductor. And therefore, we can see that we have a spherical waveguide formed by the Earth's surface and the ionosphere surface. And therefore, we shall see that when we can use this to guide radio waves around the Earth with no whatever, okay, without reflection, without attenuation. And therefore, we can allow for large or large distance communication. That is, you can talk to anyone around the Earth when we use it as our waveguide. And that brings us to the end of that particular topic. I know that was a little bit more mathematical, and I've gone through it very fast. This is given as for completeness, and therefore, if you have any issues, you can always now raise them up, as we have 5 minutes to our time. So, any questions then? What is it you are saying it's an anomaly? What I talked about, this capacitive surface? The person who is asking this question, just let me know what it is you are talking about. It's about the capacitive surface. Now, a capacitor, capacitive impedance is 1 over j omega c, all right? Yeah, just unmute yourself so that we can walk together. You have a problem with your microphone? So, okay, fine. So that capacitive impedance can be written as minus j over omega c. But when you look at this capacitive surface that we have looked at in a dielectric, we are seeing it as minus j multiplied by omega and multiplied by the other constant. So if we were to put the minus j up, or the minus aside, of course it looks like an inductive impedance. But it's not an inductor, because it has a negative impedance. And the only thing that we know has a negative impedance is a capacitance. So do we see the anomaly? Yeah, the capacitive impedance should, capacitive impedance should increase or should decrease with increasing frequency, because it's usually divided by the frequency. But this capacitance that we have now is increasing with increasing frequency. And that's why I called it an anomaly, because it's behaving like a capacitor, but a capacitive impedance that is increasing in frequency. So any other problem? So next time we are going to start now on what we call the radiation. And the way we are going to attack radiation is that we are going to assume we have an open circuited transmission line, and then we want to drive it and see what happens at the ends of the transmission line. Remember, if we are using perfectly conducting conductors for that for the wave line, for the transmission line, then the electric field must be everywhere normal to the surface of the conductors. And therefore we see that at the end, at the open circuited end of the guide, the electric field will try to approach the two conductors at 90 degrees, and therefore there will be bulging out of the fields at the other end. And that's what we call fringing effect. And therefore, those fields that are really going very high up, very bending so much out of away from the guide or from the conductors, will come a point where they get detached from the conductor itself. And if they are detached, they form closed lines or flux lines, which will also generate magnetic flux lines, and those ones will generate another closed electric flux lines, and we already have a wave propagating away from the guide. Okay, so that is the beginning of what we call radiation. And that will be a topic of tomorrow. So that is a good thought to have in mind. So I don't know whether you guys are working on the tutorial problems that have been made available for you. Yeah, anyone with a good mic?
Yes.
Try to look at those, work with the tutorial problems I've given. Most times you'll find that any questions that you can be asked in an exam basis will not be so different from those kind of things. It's always about understanding understanding the question itself and knowing what it is. What I've noticed is that there are some people who, when they are sitting an exam, epsilon r and mu, or epsilon and mu now become like they are the same. And they use them interchangeably, and I wonder why this is the case. Okay, and this is just because of panic. We usually don't have any problems with whatever. When you are dealing it with class, you find that you are using the correct values. But when you now sit in an exam, you start now making mistakes and, you know, changing their meanings. And this one is usually taken as lack of understanding. Very. So please be careful when you're working with this, and remember when you're dealing with the transmission lines, remember that sometimes when you are looking for line lengths, the line lengths must be positive, and sometimes you may get a value that is negative. That is an angle or an electrical length that is negative. Therefore, remember you must add a pi to it, okay? Because the tangent is always a periodic and has a period of pi. So if you get a negative electric length, you should divide that one by, or you should add a value pi to it, or an electric length pi, and then you'll get a value between pi and 90 degrees, so to speak. Sometimes if the real part and the negative and the imaginary part are both negative, remember the tangent is going to be positive, but you must add pi as well to it, and therefore it will be between 270 and 180 degrees. So that's something you have to always keep in mind, especially if you get a problem asking you for the length of a transmission line that will be required to perform a given whatever function. Okay, so with that, then let's meet tomorrow and we'll talk about the radiation. And then we must start thinking about when do we want to sit our CAT. Although we've been told that the CATs will be done face-to-face, and therefore we are still waiting, but we can always give you an exercise to do online. And please don't do what you did the last time, that is copying from one another and copying the wrong things. So if you just have that as food for thought, just think about it. We can thrash that out in the coming weeks. So with that, then I'll assume that there are no more questions, and therefore I leave.
Thank you.
Do have a nice day.